In this chapter, we'll be talking about special continuous probabilities, specifically the exponential probability. Now, this is a continuous probability that characterizes the time until a given event occurs. We define lambda as the average number of events occurring in a unit of time. Now, this is the same parameter as in the Poisson probability. So, whenever we have a continuous random variable, say x, and it's distributed with an exponential distribution, we write it like this. X is distributed with an exponential distribution with parameter lambda, where lambda is greater than 0. Now, lambda is always greater than 0 because we're dealing with time. And sometimes we can see that instead of lambda, we can see the letter theta. Now, this probability distribution must be specified in the exercise, or it must be stated that the number of events in a given unit of time has a Poisson probability, in which case the time until the next event has an exponential probability. Now, this is a connection between the Poisson and the exponential probabilities. The density function of the probability distribution is this. This is small f of x, and that equals to lambda times e to the power of minus lambda x, for x being greater or equal to 0. Now, what does this function look like? Okay, so here we have x, and here we have f of x. Okay, now when x equals 0, okay, we'll just plug in 0 here. That'll be lambda times e to the power of 0. Now, e to the power of 0 is 1, so that'll equal to lambda. That'll be equal to lambda. Now, what happens when x goes to infinity? Well, e to the power of minus lambda x, right, goes to 0. Okay, so that means that this is a monotonously decreasing function, right, until infinity, where at infinity it equals 0. Now, what about the cumulative distribution function? Well, that's big F of t, and that equals to the probability of x being less than or equal to t, and in our case, right, that equals to 1 minus e to the power of minus lambda t. And what does this function look like? Well, again, we have here x, we have here now big F of x. Okay, now, when x equals 0, well, that means that this expression, right, equals 1. Okay, so we have 1 minus 1. That equals to 0. And what happens at infinity? Right? That means that this expression right here goes to 0. So at infinity, big F of t equals 1. So this is a monotonously increasing function. Okay, and at infinity, it'll be equal to 1. Okay, now the expectation of x is 1 divided by lambda, and the variance of x is 1 divided by lambda squared.